So in our previous lesson, where we looked at ways to kind of make predictions about the location of an image in a curved mirror, we were able to move the object and then using light rays make predictions about where that image would be and develop some rules. Now you may or may not have noticed, but over here when we look at these blue and green boxes in the bottom right corner, as I move my object, my image distance changes as well. And you might be thinking, well, how do they know that? Well, in the previous lesson, we looked at sort of qualitative, descriptive ways to identify where the image would be. So for instance, between 2F and F, or, behind 2F, etc. But today what we're going to look at are ways to take that qualitative information and make it quantitative. And that is really what today's lesson is about. So we're going to introduce you to two important equations, and they can be used for either mirrors or lenses. But what they allow us to do is to take qualitative information about the location of images formed in mirrors, or objects in mirrors, and make predictions about images, and so on and so forth. Now you might be thinking, well, how is that particularly useful? And so if you've ever gone to the optometrist, then you know that they put you through a series of tests to test which lenses will help you best able to see the letters that are on the board, on the screen. And so those lenses have very particular focal lengths in order to help you to see best. So, and that's just one example. Another example would be, developing mirrors for particular functions, right? So for instance, those makeup mirrors that allow you to maybe pluck your eyebrows, then that's just one sort of random example. So let's take a look at an equation that is really important. We're going to look at two equations separately. In the first screencast, we're going to specifically look at one called the distance equation. Okay, and so it's possible for us to make predictions about the image characteristics by looking at a mathematical relationship. So this first equation is called the distance equation. So let's take a look at it. It reads as 1 over f equals 1 over di plus 1 over do. Okay, and let's look at the meaning of each of these variables. So f in this case is a lowercase f. And when we see that lowercase f, that refers to the focal length. And so I'm going to explain what each of these variables are in a diagram in a second, so just stay tuned. So notice the d for both of these. They're both d's, so they represent a distance. But the little I in the subscript is telling us that that in particular represents our image distance. Okay, and the little subscript O in this case represents the object distance. So in other words, these are asking us, well, how far is the image from something? Well, what would be that something in this case? That would be the mirror. So the image distance is essentially how far is that image away from the mirror? And the object distance would be how far away from the mirror is the object. Okay, let's visualize this. So here I have a standard light ray diagram similar to the ones we would have seen yesterday in our lesson on concave mirrors. And here we can see that there is an object. I can tell this is the object because my incident rays are leaving the object. And I can tell that this is my image because the reflected rays are meeting at that image point right there. They're converging. So let's take a look at what some of these variables would be on this diagram. Well, the focal length would be this distance from my focus to the mirror along that principal axis. So this distance right here is what I'm talking about when I talk about the focal length. Now my object distance would be the distance represented by this incident ray here, okay, parallel to the principal axis. Okay, so how far is that object away from the mirror? And then my image distance would be the same, just for the image, right? How far away is that image from the mirror? So there are a couple of other details that we need to make sure you understand before we dive into a word problem on all of this. Now, you may have deduced this already, you may have figured this out, but I'm going to make it clear because it does become important in some of our problem solving, that the radius of curvature, that is C, is always going to be twice the focal length. So for instance, if I know, for instance, that right here, this focal length is 5, then automatically I know that C, my center of curvature, is going to be twice that, is going to be 10 centimeters for argument's sake. Okay, so that's an important mathematical relationship for us to keep in mind as we're problem solving. So there's even more important detail, I feel, is that we can, just like on a graph, you know, in math where you have positive and negative x values, in optics, we consider the values that are in front of the mirror to be positive distances and values that are behind or inside the mirror to be negative distances. So for instance here, I can see that in this convex mirror, I can see that my object is in front of the mirror, and so it would have a positive distance value. I can see that my image, however, is behind or inside the mirror, and so it would have to have a negative distance associated with it, right? And then, of course, and this won't be told to you explicitly in a problem necessarily, but if you're dealing with a convex mirror, you're going to have to remember that that convex mirror has its focus behind the mirror. And so the focus, the focal length, will have to be a negative value for that. But we'll look at an example that will help to remind us of that. And again, that is because this, you know, this convex mirror is a diverging mirror. And so the diverging rays will never meet on the real side of the mirror. They'll only meet behind the mirror, in which case that is a negative distance. Okay, let's dive into a problem. And so quickly before we start problem solving here, I want to remind you of the GRASP method, right? And so in grade 9, hopefully when you managed to work through some density problems, you may have been introduced to the GRASP method, which basically is just a way to structure problem solving so that you're showing all of your work and you're being thorough in your analysis. So we're going to do a modified GRASP method here when we're solving our word problems in optics. So usually I find that the best way to start a word problem is to extract all of the given information, the information given to you in the problem that will help you solve the problem, right? So just writing out all the information that's given to you, right? And then also along with that, the required, right? So what is it that you're looking to find? Okay, the analysis part is, well, what tool are you going to use to solve that problem? What formula makes the most sense to make use of to find your unknown? Okay, your solution is where you input your givens in an effort to find your required variable. And then finally, writing some sort of a therefore statement is an appropriate way to conclude a word problem. Okay, so we're going to keep that in mind and do a modified version of that as we work through our problems today. So I may not explicitly outline each of these variables, but they will be there implied in my solution. Let's get started. Okay, so let's read through this problem together. It reads, an object is placed in front of a concave mirror. An object placed in front of a concave mirror is 10 centimeters from the mirror and produces an image that is 20 centimeters in front of the mirror. Calculate the focal length and the radius of curvature. Okay, so I would suggest at this point that in questions where you're looking at something that's very visual, and we're looking at images and objects in mirrors, so that is, to me, speaks to something very visual, that it makes sense for us to have some sort of a diagram to help us create this, visualize this a little bit better. And so this diagram doesn't need to be anything super special. You know, I'm just going to kind of give it a rough go here. I've got my principal axis, and, you know, I'm just going to create, it's a concave mirror, so I'm drawing my mirror as concave. Now, a couple things I need to be thinking about right now, which is that because this is a concave mirror, I'm going to expect my focal length to be a positive value. It's going to be on this side of the mirror. So I'm already sort of making these predictions about whether what my answer should look like, right? We don't want to just kind of take for granted our answer. We always want to make sure that our answer makes sense. So I've sketched up my concave mirror because the question says, first of all, concave mirror. Okay. And it says to me that my object is placed in front of the concave mirror, it's 10 centimeters from the mirror. So I can actually do kind of a couple of things at once here. I can say, all right, well, that tells me that, you know, DO is going to be 10 centimeters. And in fact, I can kind of, you know, sketch that up if I want to. So I've got, you know, here's my DO. This is my object. And, you know, I know that this distance right here is going to be 10 centimeters. And then so it says to me next that it produces an image that is 20 centimeters in front of the mirror. All right. So, you know, that tells me that my DI is at 20 centimeters. Right, so I can go ahead and I can sketch that up. And that my image is going to be, my image distance is over here, so that means, you know, this distance here is, you know, 20 centimeters. Right? And so now, usually, the last sentence in a word problem often gives you clues about what it is that you're looking for. So it says, calculate the focal length, right? So that means that my unknown in this case is little f. So I've done all my setup. This is the setup that I have for my problem, and so I am ready to solve it. Okay. So what I'm going to do is I'm just going to create a little bit of space for myself. I'm going to get rid of this diagram because I want to have some space to make this solution nice and clear for you. Right? So, you know, analyzing what we've looked at so far, I know what DO is, I know what DI is, and I'm looking for F. So I've got my givens and I've got my required to find. Now I need to know, well, you know, what is my analysis? You know, what do I need to use? What tool do I need to use? Well, so far the only equation I have is my distance equation, which is 1 over F is equal to 1 over DI plus 1 over DO. And so I'm going to start by just simply substituting in those values, right? So 1 over F is my unknown. I don't know it. I'm going to put in 1 over 20 and then 1 over 10. Now, what we're going to do in this case is I'm going to show you how to solve this by, these are fractions, and so we're going to use a common denominator to try and get this solved. But then what I'm going to do is I'm going to show you an easier way to solve this using your calculator. Because I want your understanding to be twofold. I want you to understand how the math works, and then I want you to be able to use a tool to solve this efficiently. Now, these numbers are nice and friendly numbers, but remember that, you know, these distances don't have to be nice whole numbers. They can be decimals and so on. And so sometimes those numbers are a little bit more cumbersome to work with. Okay, so remembering that when I want to add fractions where the denominator is not the same, I need to make sure that the fractions do have a common denominator. And so what I'm going to do is I'm going to change the common denominator to 20. So I'm going to multiply this by 2 and then this by 2, and that will give me a denominator of 20. Let me rewrite that. So 1 over F is equal to 1 over 20 plus 2 over 20. Just remembering that whatever I do to the top, I need to do to the bottom so that my fraction remains equivalent. Okay, and so now when I, as a quick reminder, when I add fractions, I go numerator to numerator. Those get added, but then I keep my denominator the same. And so 1 over F is going to be equal to 3 over 20. Now, I could evaluate this, but I'm not going to at this point because I want to explain a little bit more about how and why this particular solution and method works. So I'm just going to cordon off that. Now, if I know that 1 over F is 3 over 20, it should seem reasonable to me that if I take the reciprocal of both of these sides, that the reciprocals should be equivalent to each other. So I'm going to do exactly that. So the reciprocal of 1 over F is simply F over 1, right? F over 1. And then the reciprocal of 3 over 20 is just 20 over 3, right? Now, f divided by 1, I can just kind of get rid of that 1. I don't really need it there. And so by taking the reciprocal of both of these sides, I now have a value that I can solve for to, to get my focal length. And I'm going to do that. Excuse me. So 20 divided by 3, give me my answer. And so, I'm not going to worry too much about sig figs here. I'm going to round this to 1 decimal place to give me I'm getting 6.666 whatever, so 6.7 centimeters, and that is my focal length. So if I wanted to, and I have the space to do it, I'm going to write, therefore, the focal length is 6.7 centimeters. Which would mean that in that diagram that I drew, I would be able to locate my F along the principal axis. Now, some of you who are not really super math keen are probably a little bit overwhelmed right now with this business about fractions. So what I'm going to do next is I'm going to show you an alternate way to solve this using your calculator. So stay tuned for that, and it will simplify things a whole lot for you. So what I have here is the same, substitution that I saw in the problem on the last slide. But what we're going to do instead is we're going to grab our calculators and we're going to input this into our calculator, right? So here's what I need you to do. So we've substituted in the values correctly. Remember that anytime I have a fraction like 1 over 20, that really just means 1 divided by 20, right? And so we're going to use a combination of division and using brackets and addition to figure out what 1 over f is. So that is going to be my goal. And so, here's the sequence of steps. This would be a lot easier in person, but we're going to do our best here. This is the sequence of steps you're going to use. You're going to go 1 on your calculator, and then go divided by 20. And then plus, and then you're going to need to put brackets. You're going to need to use those brackets symbols to open the bracket. And then you're going to do the same with the 1 and then divided by 10. And then I'm running out of room here, but then you want to close your bracket and then go equals. So let me just review that again, because that's a lot. You're going to go 1 divided by 20 plus, and then use your brackets, 1 divided by 10, and then equals. Okay, go ahead and type that in and make sure that you get the answer that is the same as mine. And if not, this is maybe an occasion where you would want to reach out on a Zoom meeting so that we can sort this out. So 1 divided by 20 plus, and then I'm going to use my brackets, 1 divided by 10, and then close your brackets, and then equals, and you should end up with 0.15. And we're sort of keeping in mind that the last time we solved this problem, the answer we got for our f was 6.7 centimeters, right? And this most definitely is not that. But remember, we haven't solved for f. What we've solved for is 1 over f. So what I'm going to introduce you to right now is a button on your calculator that will allow you to solve for f by just simply pressing a single button. Okay, and so I'm going to switch to the next slide here and show you a couple different possibilities you might see on your calculator. Okay, so what you're looking for is you're looking for the button either 1 over x, right, which I can see right here. Okay, sometimes it's on the second function. You have to look for it above. In this calculator, a lot of you have this one, which is why I chose it. It's kind of like hidden above the 2, and it's the x to the -1 button. So it may not be in this location, but you're looking for one of these two buttons, the 1 over x or the x to the -1 button. Now both of those are the reciprocal function. So what they have the ability to do is to take the reciprocal of any value that it is that you found. And that's exactly what we want to do. We want to find the we don't want 1 over f, we want f. So we need to take the reciprocal of 0.15. And so what you're going to do is you're going to just take the answer that you get that should hopefully still be in your calculator, and you're simply going to go ahead and you're going to press either the 1 over x button or the x to the negative 1 button. And when you do that, you should get that f is equal to 6.7 centimeters. Okay? So again, if you're struggling with that aspect of how to use your calculator, that's an opportunity for you to reach out on Zoom, and we can sort it out one-on-one using the whiteboard and using our video function, and we'll get that cleared up for you. Okay, let's try another question. Okay, so in this example, it says a concave mirror has a focal length of 12 centimeters. And the object is placed 40 centimeters in front of the mirror. Calculate the image distance. Okay, so what I'd like you to do at this point is to pause the video and get your setup done. Okay, in other words, maybe draw a nice diagram to help you visualize this and write out all of your givens. By going through this process, it will help you to engage in the problem solving process, and then it'll kind of help to strengthen those neural pathways and strengthen your problem solving abilities. So take a minute to do that, and then we'll come back with all of that information ready to go and ready to solve. And if you're comfortable, go through and solve the problem. Give it a go. Okay, so it says here I have a concave mirror. So my instinct is as soon as I see that, I'm going to draw it out. Concave mirror. With a focal length of 12 centimeters. Okay, so that means my focus is going to be here, you know, and the distance between it and the mirror is going to be 12 centimeters. So there's 12 centimeters, right? And I can write that out as a given. So my F is equal to 12 centimeters. Okay, now it says an object is placed 40 centimeters, so like way off in the distance here. You know, this is just not being specific, but way off in the distance, you know, I've got, you know, my object at 40 centimeters away. So that is DO. And so it says calculate the image distance. All right, so that's telling me that DI is my required to find. I don't know what that is. So hopefully you did okay with that, just doing your setup. So now I'm ready to incorporate my problem solving skills to help me work through this. And so I'm going to just create a little bit more space for myself by getting rid of this diagram. Right? And again, you know, writing the diagram is helpful because I know that if I have a concave mirror, that my focal length is going to be a positive value. So that just further helps me to remind myself, well, where is that focus in this mirror? Okay, so moving on to my solution. So 1 over F is equal to 1 over di plus 1 over dou. And in this case, it's my DI that's my unknown, right? So I'm going to sub in what I know. 1 over 12 is equal to 1 over DI plus 1 over 40. Right? So now, since my unknown is, you know, right here in, right there in that denominator, and it's on the raw, it's not isolated on its own on one side of this formula. What I need to do is I need to isolate it. So what I'm going to do is I'm going to move this plus 1 over 40 to the other side of this formula so that I can isolate 1 over di. So let me do that, and I'm going to rearrange this. Right? So I've got 1 over 12, and then when I move this over, I'm subtracting it now. Minus 1 over 40 is equal to 1 over di. And so now at this point, what I want you to do is I want you to attempt to type this into our calculator using that 1 over x function or the x to the negative 1 function to end up with your solution. And then, you know, just make sure you can follow through these steps with us. So I'm going to do the same thing here. So I have 1 divided by 12 minus, I'm going to use my brackets here, 1 divided by 40. close bracket, equal. And so for 1 over di, I'm just going to write this just in, so 1 over di is equal to 0.0583, and so on and so forth, right? But I don't want 1 over di, and frankly, like, this doesn't really make a whole lot of sense. And so here's where I'm going to just simply press my 1 over x button, and I'm getting that di is equal to 17.1 centimeters. So hopefully you did okay with that as well. So di being 17.1 centimeters, I'm going to therefore write my little therefore statement. Therefore, the image is located at 17.1 centimeters in front of the mirror. Now you may be saying, well, how do I know it's in front of the mirror? Well, I know it's in front of the mirror because it's a positive value, right? If it were negative, then that would tell me it was behind the mirror. I also just wanted to take a minute to kind of relate our answer in this last problem to what we already know from just knowing how to predict our image location. Oops. Sorry about that, some just little technical issues. So in the last problem, we said that our focal length was 12 centimeters, and our object distance, right, it was like way the heck back here, right? So I can't even really put it on this diagram to scale in any way, shape, or form. But, it was located at, 40 centimeters away from the mirror, right? So in other words, behind C. And how do I know it's behind C? Well, if F is at 12 centimeters, our center of curvature has to be twice that, so at 24 centimeters, right? And so if our object is at 40 centimeters, it's well behind C. Well, what do we know about where the image is going to be if my object is behind C? Well, I know that my image should be between C and F. And in this particular problem, we got that our image distance was like 17-ish, right, centimeters. So that's an answer that kind of aligns with what we know we should expect for a problem like this. Okay, let's try one last problem before I send you to work on some questions for practice. And so this problem I would like for you to try entirely on your own before you come back and we look at the solution. So I'm just going to read through it with you, and then I want you to pause the video and get going, and then resume the video when you're ready to take the question up. So it says, a convex mirror has a focal length of 6 centimeters. An object is placed 8 centimeters in front of the mirror. Calculate the image distance and decide if the image is real or virtual. Okay, so that's going to demand a little bit more of you. I'm curious to see whether you will make the connections that I'm hoping you will make. Pause the video and resume when you're ready to see the solution. Okay, so I'm going to take this problem up now by starting to extract information from the problem itself. So first of all, this is telling me it's a convex mirror. So convex mirrors, we need to be remembering something about the focus. So let's draw that out to help you remind yourself of this. And if you got this piece wrong, not all is lost. You'll hopefully remember this when working through other problems. So here I've got my convex mirror. And I know that a convex mirror is a diverging mirror, which means that any light rays that hit the surface, any incident rays are going to reflect and diverge, right? So what that means is that my focus is behind the mirror. So my focus right here is behind the mirror, which means that my focal length in this problem is going to have to be a negative value. Now the question doesn't tell me that. That's where the drawing this diagram helps me to remind myself of that. Okay, so I have an object that is placed 8 centimeters in front of the mirror. So that is my DO. And it says in front of the mirror, so that value is actually positive. Right? Now, before we begin, so I'm looking for my object, my image distance. And I want to remind you, in a convex mirror, right, the characteristics of the image are such that that image should always be virtual. It's always going to be behind the mirror. So how am I going to be able to prove that? Well, mathematically, I'm going to anticipate that my DI is going to be a negative value to indicate that it's behind the mirror. But let's just see. Let's just go through the motions and see. So those are some anticipation pieces. It's almost like I'm hypothesizing in a sense. So let me go ahead and start to solve this by setting up my analysis. So 1 over f is equal to 1 over di plus 1 over dou. So 1 over negative 6.0. And I'm going to type that into my calculator eventually, the same as I always would, using that negative, but I just need to put a negative in front of the value. So 1 over di plus 1 over that 8.0. Right, so I'm going to isolate 1 over di first by bringing this plus 1 over 8 to the other side. And now I'm just going to rewrite that. I'm running out of a little bit of room here. So 1 over negative 6.0 minus 1 over 8.0 is equal to 1 over di. Right, and so I'm just going to cordon off some area here for me to write my solution. And so I'm going to simplify this little business right here, and I want you to do the same. And what we're going to end up with is something that represents 1 over di. Okay, so let's simplify this business and end up with 1 over di, and then we'll get to di in a moment. Okay, so 1 divided by negative 6 minus 1 divided by 8. Using my brackets, I'm ending up with negative 0.29 when I round that roughly. And so now's the point where I'm going to use that x to the negative 1 button, right, or my 1 over x button to end up with the reciprocal. And when I do that, I am ending up with di being equal to negative 3.4 centimeters. And again, I already knew, I expected that my image would be somewhere behind the mirror here, right, at negative 3.4, right? So the negative here makes sense because that image is indeed behind the mirror. So finally, I'm just going to squeeze in a therefore statement. Therefore, the virtual image is 3.4 centimeters behind the mirror. Behind the mirror. Okay, so again, how do I know it's virtual? Well, it's behind the mirror, right? It's inside the mirror, which makes it virtual and not real because the light rays that would have formed it are forming, you know, from those dotted extensions behind the mirror, the virtual lines. So hopefully you did okay with that problem. If there's any issues with respect to solving it, then just make sure you reach out. What you're going to be looking for in our unit plan right now are some questions that are dedicated to the distance equation that are meant for hand-in, and so I would like for you to spend a little bit of time working on those problems before moving on to our second screencast, which will discuss the magnification equation. And again, yeah, reach out on Zoom if you have any problems whatsoever, and I'll be happy to clarify or work through a problem with you.